So, dear participant, thank you for joining the session. First of all, I would like to welcome all of you who has given their time to attend this webinar sessions. So, I would like to invite our speaker, Ms. Arti Dixit. She is from Berhampur University, working as a research scholar. So she is working on SETFOS software, specifically on perovskite applications. She joined with us. So first of all, she will deliver a small talk about their research papers, where she will explore about their papers ability and will show you how this kind of research paper she has published in good journal by using SETFOS software. So I would like to thank you, Arati Dixit ma'am, to join the session. Now I would like to request you to kindly share your screen and would like kindly please give a small brief talk about your work. So thank you. Now it's over to you.
So, good afternoon all.
Yes, very good afternoon, ma'am. We can hear your voice.
Okay, good afternoon all, and I want to thank Anil sir for the introduction. So myself, Arati Dixit, I am a research scholar working presently at Berhampur University, Odisha, and I am working under the supervision of Professor Kumar Tripathi, who is also belonging to the Department of Physics in the Berhampur University. So presently we are working on Perovskite-based solar cells, and SETFOS is the software that we are using for our simulation purpose. And this Berhampur University has a center of excellence that is for nanoscience and technology for the development of sensor, and that is the center where I am presently working and where this SETFOS software is also installed. So today I will be talking about my works, including the outline. It will have introduction part. Then I will overview about my research work, which I have done using the SETFOS software. Then also I will discuss about my works that are based on particularly methylammonium perovskite solar cell, and also another perovskite Azetidinium as the active material for solar cells. So coming to the introduction, since these solar cells, we know that they are nothing but basic of solar cell is this forward biased PN junction diode. As you can see here, any perovskite solar cell or any other solar cell, we can have a photoabsorber material, which is the active material. Then we need to have carrier collectors so that we can collect the carriers, which are electron and holes generated by the absorption of photons. Then also we need to have metal contacts so that we can transfer the carriers generated into the circuit. So any solar cell, you say this is the basic structure of any solar cell. You can see here we have a region which creates the holes and electrons upon incident by sunlight. So these electron and holes, they are going to travel in opposite directions or directions as we have made the solar cell in that way, so that electron collector layer is there, which is collecting the electrons, and there is a hole collector layer which collects the holes and separates the charge carriers through the metal contacts, so that in the external circuit we can store energy or use the energy as the photovoltaic energy. So in any solar cell, we can have a very important graph, that is the IV graph or JV, or sometimes you can take current here. Also you can take current density, which is J, and the voltage is taken along the x-axis. Then this plot is the IV plot, and it is the most important curve in the function of any solar cell, because here in this curve we have certain photovoltaic characteristic parameters can be determined, like the VOC, which is the open circuit voltage, which gives the value of voltage at which the current becomes zero, which is here, we can see from the graph. Similarly, another important quantity is the JSC, which is the short circuit current density, and that can be determined from the ISC, which is the current when the voltage is zero. So again, another important photovoltaic parameter is the fill factor, denoted by FF. This fill factor is actually a percentage of the area under the IV graph, which is close to the rectangle, forming the sides with IMP and VMP. And this P in is the power input, which is the power of the sunlight or power in the photon of the sunlight. So using these four parameters, we can calculate a quantity, that is the photoconversion efficiency of any solar cell. So this photoconversion efficiency gives the idea or gives the basic thing that a solar cell will work how much efficiently. So whenever we talk of a solar cell, we need to have this efficiency as high as possible. But since there is a limitation to this efficiency, so we will work on the improvement of the efficiency under the available situations. So since there are a lot of variety of photovoltaic solar cell possible, depending on the nature of the active layer or the photo absorber layer, we are currently working on the particular type of solar cell where the active layers are perovskite layers. All of you must have listened about perovskite solar cell because they are very popular in the research field. So all these things we will do, but before that we need to find the best possible configuration for any device. So before going to experimentally fabricate any solar cell, one need to have a strong available in data, so that we can get a very good solar cell while performing or while doing in the lab. So we have used a software that is called SETFOS, and it is a very good software provided by Pluxim. And this software helps us to gain the insights into all the insights about the various parameters of a solar cell before going to the lab. So this software is actually stands for Semiconducting Thin Film Optics Simulation, and this can be used for the simulation of solar cells along with LEDs. But we are currently only in our lab, our group is currently focusing on the solar cell part. So other groups are there, those are doing the LED parts, but I will talk only about the solar cell part. So this SETFOS has very good advantages, like it has very user-friendly graphical user interface. Using this is very easy. Once you have a small tutorial, you can get acquainted with it, and it is easy to use. So here we have intuitive access to the device structure and the material parameters, and it also contains files in its database so that we can use directly the data if we have the material already in the database. Also, the output of the simulation is also in the form of graphical, and along with we can transport or we can also import the data into other graphical softwares and use them and analyze the various data. So basically this SETFOS has various modules, like we have emission modules, and we have drift diffusion module, and we have optics module and absorption module. So in case of solar cell, we are currently using these three modules, this drift diffusion, absorption, and this scattering module. These three are combinedly used. You can use them separately also, depending on the purpose. Then we have also a sweep function available in SETFOS. Using this sweep function, we can sweep the parameters as we wish for the maximum efficiency, and we can get the value of that parameter which is most suitable for our purpose. So that is a very important function of this software, which we have been using and published few journals in the international reputed journals. So these are the basic features or key advantages the SETFOS software has. So let me go to the work which we have done using this SETFOS. So first I will discuss about the simulation work that we have done taking methylammonium as the perovskite material. So since perovskite is very popular because of their properties, like they have a band gap which is tunable, or we can change as per our wish within a certain range. They have very high absorbance. So the photon absorbance rate efficiency is very high. And they have low excitonic binding energy. And the electron and holes, they have high mobility, long carrier and diffusion lengths. And they have also easy fabrication methods. So because of all these advantages, these perovskites are nowadays very popular in the field of solar cell as far as research and development is concerned. So let me tell you about basic structure of any perovskite. So when we say perovskite, it has a particular structure that is called as ABX3 structure. Here, this ABX3 structure stands for, here A stands for a cation, which can be of the type methylammonium CH3NH3 group. It is a cation group. Here you can see the structure is like this. So this cation can be taken as the A site, or other cations also can be taken. So if we take this one particular, so this perovskite is called methylammonium perovskite or MA. Then in the B site, we have also another.
Excuse me, ma'am.
Yes.
Ma'am, your screen is not visible now.
Earlier it was visible.
Yes, ma'am.
Is it visible?
It's visible for me.
It's visible.
It is visible. Yes, it is visible.
Okay, sorry.
Okay.
You can continue, ma'am, please.
Yes. So this B site, we have also another cation present, which is smaller in size than the A site. And this cation can be either lead or tin. And in the X site, we can have halides like chlorine, bromine, or iodine. So this particular kind of cubic structure is called as perovskite structure. So we have taken, coming to particularly to my work, which is published in 2023. So we have published this work taking this perovskite as MAPBI3, and this is the structure of the layer structure of our solar cell. As we have one glass layer, which is the ITO layer, transparent conductive glass, and then we have taken NiOX nickel oxide as the HTL material, hole collecting material, and this is our active region. And PCBM is a material which is taken as ETL or electron transport layer. And this silver we have taken as the back contact electrode. Now we have simulated this structure by taking all these parameters from various reported results. Then we also have added another layer as compared to the figure A, another layer PBS, that is the lead sulfide layer, is added here in the structure B and C. You can see PBS present here. So basically our paper is a comparison paper which compares the efficiency of this structure with these two. So the effect of addition of this PBS layer was studied using SETFOS. So we have studied the various parameters and we have optimized the layer thicknesses of the perovskite in this way. Using SETFOS, we can do that. There is an option, we can change the thickness of any layer and sweep that layer, and we can get the maximum value of the or optimum value of the thickness, for which we'll get maximum JSC or maximum VOC or maximum fill factor, and as a whole, what is the maximum PC we can check. So this study we can do easily using SETFOS, and it is already done. Then along with that, we have also studied the effect of PBS layer thickness on the solar cell parameters like JSC, POC, fill factor and PC. So here you can see that the maximum PC corresponds to a particular thickness of PBS layer. So when we find that, we have to go with that thickness so that we can get the maximum efficiency out of the material. Then the final result, we have the JB curves for all the three structures, and this is the power conversion and voltage curves for the three structures. And all these graphs can be obtained easily using the SETFOS. So we have also this SETFOS calculates the final value of PC. We don't need to calculate this. If we put all the inputs, then automatically it gives the values of all these parameters. So you can see that when we take the bare MAPBI3 only, we have PC found to be 15.26. But when we use the PBS layer, we have an increase in the PC, one for 18.74, and another case it is 18.04. So this work has been published. Then coming to another work, which is also published in the year 2024 in Optic journal. So this work is actually done by some co-workers. So they have done the similar kind of configuration, but the active material is slightly different here. Here they have taken methylammonium, then tin iodide. So as I have said that in a perovskite material, this is the B site, and B site can be either lead or tin, or other possibilities are also there. So because this lead is actually slightly toxic in nature, so in this work they have taken this SN or lead or tin instead of lead, so that it will be less toxic or non-toxic. And in case of in the cationic, in the anionic side or halide side, they have chosen this I3. So there are a variety of perovskite we can choose. First in the first paper we have taken MAPBI3. Here it is MASN-I3. So in this simulation, the work is done in the way that we have taken the ETL, the HTL material to be fixed and ETL to be varied. So a large number of selenoid and sulfide materials were chosen. You can see these are the selenoid and sulfide materials, which are called chalcogenide materials. So ETL are varied, the material of ETL is varied, and the study is published. So let us see, let me go into detail what study we have done using this software SETFOS. So when we take the same ETL, same HTL, and ETL is changed, the plot of current density and voltage is like this. So we can have an idea that which material gives the best performance by calculating the efficiency in each of the case. Then we can also have a provision to find the values of power conversion efficiency as a function of doping concentration and along with as a function of the thickness of layer. So that is done in this research work. We have taken the power conversion efficiency for different doping concentration of the layer. That is the SN2 is the ETL layer, and at different thicknesses also we can study it. So simultaneous variation of two parameters can also be done using SETFOS, so that we can get a better idea about which value we should take. Similarly, we can also simulate the power conversion efficiency along with the active material doping concentration, taking different thicknesses of the active material. So these things actually can be done very easily using this SETFOS software. Only you have to give the information in the sweep settings and the output will be ready. So in this work also we have simulated or varied the absorber trap density. There is a provision to provide the trap density parameters in the SETFOS software. So that also we have done and checked the maximum or the optimum value of absorber trap density so that we get maximum PC. And it is the variation of the trap density in the ETL layer. This is the absorber layer trap density, and this one is for the ETL layer trap density. So along with this, we have also used the variation of work function of the electrode in this case. So since we have used gold as the electrode, bottom electrode, by varying the work function of gold, we can check that which value of work function gives us the maximum efficiency. Then also we have taken the work function of the top electrode here, and various parameters are studied under the variation of work function so that we can get the best out of it. Thereafter, the series resistance of the device or the solar cell can also be varied, and its effect on the parameters can also be studied like this. Parallel resistance can also be varied, and the best value of parallel resistance can also be checked. So this is the final configuration of the device, which is having MaSni3 as the active layer, and this is SnS2 is found to be the best material for ETL in comparison with other chalcogenide materials, and Cu2 is taken as the HTL in all the cases. So in this work, only this parameter is varied, this material is varied, others are kept constant. And along with, when we take this same material SnS2, initially the device shows the efficiency of 27.04, which is this given by this red curve in the JV curve. But when we optimize the different layers thicknesses using SETFOS and also optimize the various trap parameters, various electrodes, value of work function, and finally set the values, then we have a gain in the efficiency from 27.04% to 31.51%. So this is a very good value of efficiency as per previous records. So this work has been published. So these all works are on the Ma-based perovskites, that is the methylammonium-based perovskites. Next, we have also done another work using a different perovskite that is called Azetidinium. So this is called as AZ also. So here in AZ Perovskite Solar Cell, we have Azetidinium ion as the cation, as the A side cation. So this is the structure of Azetidinium ion. This is a organic cation, large organic chain cation. And this is the whole structure of perovskite. So here we have taken Azetidinium as in the A site, and we can take lead or tin in the B side, and in the halide site, X site, we can take either chlorine, bromine, and iodine. So in this study, what we have done, we have taken all the possible configuration by taking this B. In the B site, we have 2 options, and in the X site, we have 3 options: chlorine, bromine, iodine. So all the possible combinations were actually taken, and for each of them, we have done the simulation work. But before that, before going to the simulation part, we have done one DFT calculation, so that because this Azetidinium ion is very new, so we cannot get the various data that we are going to use in the SETFOS as input. So whenever we are using SETFOS, we have to find certain data so that we get them, we put them as the input. So since this material is very new and no more, very few literatures are available. So what we have done, we have actually taken this Azetidinium and in the DFT calculation and calculated all the data that we require for the input, like its band gap we have calculated by different combinations of these 2 and this. And then we have calculated their tolerance factor. Then we have calculated its optical properties like absorption and its refractive index, all the things we have calculated. And finally, basing upon the tolerance factor, we have chosen only 4 materials out of all combinations to be suitable for solar cell application. So these materials we have found as one is AZPBI3 and AZSNBR3, AZSNCl3, and AZSNI3. So our further research work is actually based on these 4 combinations only, these 4 materials as perovskite. Then we have also chosen the ETL and HTL differently in all the cases because they have different value of conduction band level and energy level and valence band energy level. So all these things are done by taking into the consideration that the flow of electron and hole should be uninterrupted. Like we know that whenever we have a separation of charge carrier in the active layer, electrons, they will tend to go like this and hole will tend to go like this. So the alignment of energy is very important while choosing the ETL and HTL layer. So we have also meticulously selected the materials of ETL and HTL depending on these factors. Then once we decided the layer materials, thereafter we have taken the thickness of the ETL layers as a function of this BOC, JSC, fill factor, and finally PC. So all the 4 cells, they have the data of 4 cells are swept by taking ETL as a variable and various functions, fill factor, PC, JSC, and BOC were studied along with the variation in the ETL. Similarly, HTL variation, thickness of the HTL was also varied, and the photovoltaic parameters are studied so that we can get the best thickness out of our material. All these are done using SETFOS software. So this perovskite material thickness also are swept because this is the thickness of the active layer, which is very important. So this active layer thickness also is optimized using this software. Then we also have taken the variation with temperature. That is also provided with SETFOS. We can vary the temperature or operating temperature of the device and see how it changes, how the various parameter changes. So here the 4 cells are taken, and for each of them we have swept the IB parameter, JB curve, for different temperatures starting from 300 to 400 K at an interval of 10 degree Kelvins, so that we can get the best operating temperature for the device. Then the 4 final devices were found to be having this much values of VOC, JSC, fill factor, and finally these are the PC. And you can see that the PC are also not so bad. It is very good. In fact, for maximum, it is maximum for AZSNCl3, which is 26.1. So all these can be taken, all these materials. So finally, we propose that all these materials can be suitable for perovskite solar cell once we go into fabrication. Then these are the final JB curves of all the optimized devices. And we can also find the external quantum efficiency graph as a variation with wavelength in SETFOS software. So that also we have done. And this data, all this research work, actually it has been, it is under review. So maybe in next few months it will be published. So this is the work that we have done here using SETFOS, and these are the references of this work. Thank you.
So thank you, ma'am. Thank you for giving these insights about your research work that you are published and in review.
Thank you,
And
sir.
Your research is really appreciated. Now I would like to request to participants, if you would like to ask some query related to the ma'am work, you can also ask some questions related to software or their research work.
Good afternoon, ma'am.
Good afternoon.
Actually, I have a queries. First one is the software free?
No, it's not free. It's a commercial software, paid version.
Okay.
She has purchased this. Their institute has purchased this software.
Yes.
Okay. And another thing that how do you optimize this perovskite?
Optimized, actually we have not optimized the material. We have
Okay.
optimized the various properties like layer thicknesses and then
No.
concentration of doping. Then we can optimize the temperature like that.
Actually, my concern is like when perovskite is formed, after that you have taken that perovskite in a solar cell.
The solar cell formation or fabrication of solar cell part is there, but only simulation part is here I am discussing. Before
yes,
going to the fabrication part, this should be done. So
Yes,
that we cannot have to go for many trials.
Yes, I'm getting that point. Hello.
Ma'am, I ask you one question.
Yes.
How to decide which perovskite material we can use? This
Which
material based
perovskite
on
material?
yeah. How we decide this material is good for perovskite solar cell or not?
Okay, that will go. We have to go through the previous works and literatures. So based upon that, we have chosen this methylammonium as perovskite firstly. Then later on, also we can have we have proposed another like AZ. So another other options are also there like FA. There is a formamedium ion, which is also good.
There
also
is anything
photovoltaic applications.
that we can give. Just like in some cases, we can know the band gap, band energy.
Yes,
Band gap of the materials is important.
Yes, main concern is the band gap and photo absorption efficiency.
How we can get
actually
these
there is
values of the band gap?
quasi-Sockler limit. So it shows that about 1.3 to 1.6 volt, electron volt, if the band gap is, then it is the most suitable for solar cell.
Not less than
There are
that.
published papers, you can go through, search for Sockler quasi limit in solar cells.
I have one paper that takes the band gap is 1.07.
Yes, that also you can take, but the highest maximum efficiency you can get out of the material, then the band gap should be in that range. In principle, you can take any range,
Okay,
but that
about
is
that
the most
concentration,
suitable range.
about doping concentration and defect.
Yes.
About doping concentration and defect, we can able to that kind of any variation or there or any particular values range.
Yes, using SETFOS, we can change the doping concentration and
No,
see which
I am
doping
asking
gives
about
the
general
maximum.
perovskite. I am asking about general perovskite material.
Yes.
For solar cell, any particular range for that you are saying about band gap, similar
Yes.
for the defect or defect as well as for doping concentration.
Yes, that also we have to go through a number of papers, previously published papers, so that range we can test.
What is the range in this paper?
Let me show you the graphs. Like here in this plot.
Yeah, I can see it.
Yes, the doping concentration we have varied from 10 to the power 12 centimeter to the minus 3 to 10 to the power 18. Sorry, 19.
About defect,
And the defect.
defect in parameter.
Okay, we will show you. This is the trap density variation graphs.
In normally, because I'm working on same thing on perovskite also. Just
Yes.
I go through the many papers, they are taking some range. Maximum paper is taking one proper simple one values, one or two values.
That
Normally
also
10 to
you can
40.
do. If I am changing this, then I will get a sweep like this. So I can also take a particular value and simulate.
Okay.
Good afternoon, ma'am.
Good afternoon.
Ma'am, first of all, very much congrats to you for this particular research.
Thank you.
Ma'am, this paper, your study got published in some research journal or not?
Yes, we
Or
have
you are just-
3 publications till now and 2 are under review.
Okay, ma'am. Very good, ma'am. It is a very such a nice session going on from your end. It is very appreciable and hardworking concept from your end. Thank you, ma'am.
Thank you. Any questions?
No, ma'am, but I just want to know that how much time do you have required for this particular research?
Time is actually in our hand. If we give more time, then research will be more better.
Yes.
So it depends
Okay,
on
ma'am.
ourselves.
Yes.
Later on, Anil sir will also discuss about the interface and how to practically implement the data and give inputs using SETFOS.
Okay, sure, ma'am. Ma'am, and can I ask when the feedback link will be shared with us?
Yeah, we will share the feedback link after my this talk. Okay.
Okay, sir.
So,
Sir, in the chat box only.
In the chat box or maybe in the WhatsApp group from where you have got the link on
Okay,
that.
sir. Oh,
And
sure,
we will
sir.
provide you.
Sure, sir. Thank you, sir.
So thank you very much, Dr. Arati Dixit ma'am, who has given their time and give our insights about their research work. And thank you once again. Now I would like to start my session where I will deliver that how this SETFOS software can be easier to help you to build any kind of solar cell structures. Okay, so I would like to continue the session. Ma'am has given their insight about their research paper. I would like to continue on SETFOS, how it can be used. Okay, so I would like to share my screen now. So let me give you about the small presentation for 10 minutes. Then we'll go for the demo on the SETFOS live. That how you can make any solar cell structures in SETFOS. Okay. So this demo will cover the small presentation about the SETFOS and their modules, and then details insight about the features which exist inside the software. So basically the software SETFOS, which is developed by Canadian company, this Switzerland-based company, Fluxim. So Fluxim, that is Switzerland-based company, which developed this SETFOS software. So they developed the software as well as hardware for simulation purpose, as well as for characterizations. The hardwares they are also developing specifically for solar cells and LEDs applications. So they are concentrating the academic institute as well as industries worldwide. So they developed the softwares as well as hardwares. From 2006, they are developing the product. So SETFOS is one of the product. They have multiple product for solar cells and LEDs, and even hardwares are also there for IV characterization, stability analysis, degradation, and ELPL measurements. So PIOs, pillows, litos, light. These are basically hardwares. So software simulations results and hardware results can also be comparable, so that you can find how much the accuracy of the software is. Okay, so the results can also be validated with the experimental and simulations one. So this is all about the company who is developing this SETFOS. This SETFOS is specifically designed for perovskite application, organic, tandem, thin film, solar cells, and LED application. It is one-dimensional, perpendicular. It will calculate the equations for novel optoelectronics thin film devices. Majorly, you can model the structures, you can optimize the structures based on your input parameters, and you can define unlimited semiconductor layers, and you can simulate it, including it can calculate the optical properties, electrical properties, optoelectrical properties at a time, optical and electrical simultaneously. It can calculate the property, including quantum dot and nanoparticles with ray tracing and texturing. So the main domain, the software developed for these are the listed applications, where software is specifically dedicatedly designed for such application in deeper insights. Okay, so that you can work on different organic, inorganic, perovskite, including the tandem devices where multiple layers are there, two terminal, 3-terminal, 4-terminal, heterojunction, thin film, disensitized, organic photodetector, quantum dots, including LED, white LED, perovskite LED, tandem OLED, polymer LED, and some high fluorescence LED applications. So light emitting devices and light absorbing devices. These are the main specific research application the software developed for. Now, since the software is divided in module, there are 4 modules. Somebody work on optical calculation only. For those who work on optical calculation, optical analysis of the material, then our absorption module, first one absorption module is sufficient. If you want to work on optical as well as electrical, then dip to diffusion module are also required. So absorption for optical calculation, light spectrum, optical analysis, and IB calculation, electrical calculations, charge transfer, semiconducting materials, DCAC, transient simulation, then this dip to diffusion solvers is required. So both modules can also be procured simultaneously or independently. These are all divided modules. Means the software is divided in 4 modules. Whatever module is convenient according to your research, that module you can by your institute can be planned. If you want to work on advanced optics, advanced ray tracing, texturing, non-flat structure, the textured surface is there, then this advanced optics module is required. And for emitting devices, emitter application, this emission module for LED related application, it will be required. So independently or simultaneously, whatever the modules fit your research work, you can carry that particular modules for your applications. So now this is all about module. If we talk about the advantage of the software, the main advantage is called very good user interface, so that you will not need to learn any language. You have no need to learn MATLAB or Python or C. No language is necessary to learn for you. You just have to concentrate on the physics, on your theoretical parts, and then theoretical parts you can implement as an application level in the softwares. So the sophisticated user interface will be there. You can easily learn the software. It is not very hard. Within a week, you can become an expert on the software as well. We will provide you the training also if somebody get procured. The results, graphs, presentation automatically prepared and extract. The user can automatically prepare all the graphs in the visual form as well as in the raw data that can also be extracted. And PPT can also be prepared with the software. It supports not only a charge transport. Charge transport is one of them that is possible, along with ion transport. Mobile ion charge carrier is there, anion and cations with hysteresis effect. Windows, Linux, even Mac OS is also there, where you can work on any platform independent software there. Parallel computation, great convergence. Easily it will converge the material. The simulation structure within 5 minutes, 10 minutes. The algorithm which is implemented in the software, that is very fast in running the simulation on your normal computer as well. It will not require high-end cluster or high-end workstations. Simple laptop with i5 or i7, 8 GB RAM, that the software can also run. It can also simulate the planar structure, interface, roughness, textured parameter, some experimental data, AFM or BSDM, textured data you want to incorporate in your solar device structure. That is also possible. DC direct DC simulation, AC simulation, transient simulation, impedance characteristics, IMPS and IMBS, intensity modulated photocurrent, photovoltaic, spectroscopy analysis, unlimited semiconducting layers in between the electrode. You can model and simulate. So it is not restricted on particular number of layer, either 5 layer or 7 layer or 6 layer. You can define 10, 20, 30, 40, as much as the layer in your multi-terminal, multi-junction devices. You can build it and simulate, including the tandem devices where around 10, 20 layers are there. You can simulate. You can calculate the optical property of the material first and find that which material are more light absorbing. And then you can also make the device structure, and that particular material you can use in device formation and then find the total device optical properties as well. So material optical property, device optical properties. Since the technology is upgrading very fast, okay, so software updates regularly. Whatever new research are going on in solar industry or light emitting diode industries, they are developing the latest features regularly, and that's why the software you will get a good technical supports in using the software. If you are facing some difficulties when you are using the software, that technical support, features, updates, even our main parent company also provides the support if any problems are there in using the tool, including the quantum dot, nanoparticle effect, texturing, and some multiple parameter at a time you can sweep and optimize. Let's suppose if any parameter is unknown, you have no idea how much active layer thickness is, then you can set the minimum value and maximum value. And software will do the calculation from minimum to maximum with number of steps. Let's suppose from minimum 100 to maximum 200. You want to run the calculation with 10 nanometer increment of the thickness. Then at each 10 nanometer thickness, it will increment the value and it will run the calculation on different value and give you the prediction at what value you are achieving some good characteristics. So single parameter you can optimize, multiple parameter you can optimize. So sweeping optimization is there. Emitting diode application is possible where you can simulate the LED emissive property, CIE, color diagram, ELPL, electroluminance, photoluminance, and radiance. Multiple mobility models are there. Not only a constant mobility model, it supports the state-of-art mobility model, by trap model, exciton model, temperature dependent model, field dependent mobility, and different other concentration related mobility parameters are there. So you can define all those things. So few of the advantage I have listed on the presentation, but once you will explore it, then you will find a lot of other advantage are there in this commercial softwares. So this is all about SETFOS. Even we have a large area PV module application that is called LAO software. Those who want to work on PV module. For large area application, we have this LAO software from the same company that is called large area organic semiconductor device simulation software, which works similarly for LEDs and the solar cell, but at large area where you want to define some millimeter, micrometer, and would like to optimize your structure. You want to reduce the electrical losses, ohmic losses, thermal losses, optical losses, some FEM calculation, 2-dimensional plus 1-dimensional simulation. This LAO software is there. It is more advanced, the coming module application, RGB, pixel crosstalk, AMO LED application, then this LAO software will be helpful. So these are different products that we also have that I wanted to show you as a promotional purpose, so that you will have a detail about different products that our company is providing. Now, if you see on the screen, you can see the SETFOS that is already discussed by Arti ma'am, and this LAOs, PIOS, these are equipment for IB measurement and electroluminance, photoluminance, luminance measurement flows, degradation analysis of LED, stability analysis of perovskite solar cell, even atomistics, material and quantum device simulation software. We have a nanodecal, rescue, and QTCAD software that works on density functional theory for atomistics, nanoscale material, nanoscale device, and spin qubit, semiconducting quantum technology. That kind of software our company is also providing. So these are the different products that we are also offering. If any product you are interested, you can let us know. These are some current customer which is using SETFOS in India. So they have procured SETFOS from us, and we have supplied, and they are using it and publishing some papers in good research journal. Now, if I would like to go, if you have any technical questions, this is my contact information. You can drop the email or you can call me. This is my number. You can email me or call me. I can help you to provide more insight information about the software. Now let's start with the software so that you will have main things that you wanted to see it. So I wanted to open the software here, which is already installed in my computer. That is called SETFOS 5.4. I want to click on Run as administrator to give the full privileges of my software. So you can see the software is opening. The user interface is opening here. Now, whatever the new features come, that will show on top of the screen. As you can see, there is a new version of SETFOS 5.4.12 that is released. Whatever new updates are there or bug fixes are there, that will show on top of the screen. So I want to close this new feature window, and that will show here the current source boundary condition for electrical simulation that is developed in the current version. Impact ionization model to simulate the reverse bias breakdown model is implemented. AC responsibility output for photodetectors that is developed. Input file are more sweepable. You can sweep the main input file, whatever input file you want to sweep. That can be swept. More robust depth diffusion solver with increased numerical precisions, and many more features are under development. So software are continuously developed by the company. Now I want to show you the main interface about the software. This is our main user interface. Now, if you look into the interface, there is an option called help option. In the help option, there is a manual and tutorial. If you would like to get the insight about the software, there is a tutorial is there. The manual is there. In the manual, you will get the background information, the theoretical equations, the model, the algorithm, which is implemented. The equations are implemented on what basis. That information you can find in this manual page. So manual will basically give you the insight about that which models, which mobility model, which doping model, which drip to diffusion, charge transport, ion transport, or metallic work function, contact models, or drip to diffusion models. The model information, the theoretical information about the equations that is implemented in the software, that information you can get it from the manuals. So manual is provided by the company, so you can see all the equations, models with the input files and their units, that is default unit, default parameters given, implemented in the tool, that is given in the manual page. If as a beginner, as a layman, how you would like to work quickly on the software, then there is an option called tutorial. When you go to the help section and go to the tutorial, you can find this PDF page. SETFOS 5.4 simulation software for solar cell and LED, absorption, dip to diffusion, advanced optics, and emission modules. So you can go down and you can see it's one by one the content, that how you can make your first solar cell, first LED, or how you can validate with the experimental data, dip to diffusion modeling, coupling of electrical and optical simulation, physical parameter extractions. So this is bibliography. Once you will click on it, step by steps, if you will follow the tutorial, you can easily build the structures. It is simplified tutorial page. So once the tutorial you will follow, it will not take much time to use the software quickly. It is completely a very good documentation with proper screenshot and highlights are given, so that you will not find much difficulty in exploring the tool. Still, if you need any support, we have a YouTube channel and we also provide technical support to our customers. If some problems are there, you will face it. Whenever you will have any plan to purchase, then we will also provide you the training so that you will not face any difficulty in properly using the tool that you have planned to procure it. So our service is very good. Our software is very good. Only you have to explore it and find how the software is more meaningful or researchful for you. So that's why this manual and tutorial both are there, which will provide you a deeper insights about different application that the software support and different models, equations implemented in the softwares. Now, if you go to this right side on the top, toggle workspace view. In this left side, you can find couple of examples are there. Couple of examples are given related to solar cells, perovskite, tandem, thin film, organic, LED. I will scroll up, and once during the scroll up, you can find a lot of examples are given in the library. It is example library. We have a material library. We have an example library. The optical material library also there. Semiconducting material library also there. So you can see here, these are all examples related to different full solar cell application, full OLED, white OLED, and including the AC current and absorbing devices. Now I would like to open one, I would like to take one example. So I want to click on this file option and would like to start from scratch. So I click on this file option, then click on new options. So I want to give from beginning. So you can see the default empty project is created. I want to give the name of this example as a test perovskites. Okay. This is test perovskite, the name of project which I have given. Now here you can see by default there are 3 layers. Surrounding, I can mention the name of my surrounding as an example air on the top. Then my next layer is there which I can name as an example substrate. Then third example which I can take as an example ITO. Now I have to add more layers. So I can click on this add button. This is plus sign where I can add the layer. So I can click again another add layer. So there are 2 unnamed layer are created. If I click again, the next 3 layer is created. If I click again, the next unnamed 4 layer is created. To add more number of layers, I can click on this add button multiple times, and that number of layers will be added here, and it will reflect in the right of the screen. So layer structure is also reflecting in the right sides. Now this is air substrate ITO. Now here you can see the ITO is there. I want to define my other name. Let's suppose you want to define electrode transport layer. The next layer you want to take as an example perovskite layer. This layer you want to take as an example hole transport layer. And then next layer as an example you want to take aluminum layer. And this layer I want to delete it as an example. So you can see there is an option called minus, which once I will click on this minus, I can delete it. And this is my air on the bottom side. So these are the number of layers as an example I want to simulate. So as in the presentation session, I have shown you that software contains the module, absorption module, depth diffusion module, advanced optics module, and emission module. For optical calculation, I need to enable this absorption module. So once I will enable this absorption module, this absorption setting will be enabled. So this is a layer structure tab. This is absorption setting tab and output setting tabs. I want to click on this layer structure tab. You can see that each layer name I have defined. And this is the thickness of the layer. But if I want to modify this thickness, let's suppose I want to define this substrate as a 1 micrometers. So you can see I have changed the thickness of this layer, and right side, the thickness is reflecting. It is reflecting the right of the structures. Now, I want to change this my ITO layer thickness as an example. I'm taking as an example 10 nanometer thickness. I have a multiple option, nanometer, micrometer, millimeter, or wavelength respective. And this is another ETL layer. Let's suppose you want to take 25 nanometer. This perovskite layer you want to take 50 nanometer as an example. And this layer you want to take, let's suppose 20 nanometer. This is 10 nanometer. And air on top and bottom will become incoherent. Okay, that will become meaning no thickness is the meaning for top and bottom layer because it is incoherent. In between top and bottom layer, all layer become a coherent. Now we have to assign the refractive index of each layers. So to define the refractive index, let's suppose this is air on the top, which I have selected. Click on this refractive index tab, where we can define the real part and imaginary parts. So refractive index, real part and imaginary parts. If I click on substrate, the real part and imaginary part, NK data, that is given. Let's I click on this ITO layer. If the ITO layer refractive index is not constant, it is dependent on wavelength, then I can click on this file option. And here either I can create a new material here. If somebody has some data of refractive index, you have a wavelength value, and accordingly the wavelength, the real part of the refractive index and imaginary part of refractive index. Then you can create your new materials and select the NK files, where you can define your new optical refractive index as an input. As an input you can give here. So I can click on this plus sign and define the wavelength value of the first column. Second column, as an example, I want to take real part. As an example, I am taking it, but whatever the value of yours, which you have taken from some open source library or from some research paper, that value you can put it here. So similarly, you can click on again add layer. The new layer will add where you can define the first wavelength value, the second wavelength, second real part, third imaginary part. The graph will display here. Again, you can click on this add button, define the next wavelength value and real part value in the second column, and then imaginary part in the third column. So ordinary and NE and KE, that is called extraordinary refractive index. So usually we require ordinary refractive index of NK data. I have added 3, but you can add multiple times. You can add and delete the row accordingly. This is graphical script. If you want to check in the form of script, auto-generated script with the 3 value. If you want to copy paste, you can also generate the script here so that you will not have, if you already have some wavelength data and refractive index real part and imaginary parts, then you can also put it, or you can copy paste your data from research paper or some open source library here in the script. It will reflect in the graphical as it is also reflected here. So similarly, you can create your new optical material in this optical material editor window. Then you can click on OK. It will assign it. And there is an option called import. If you want to import from the library, which is installed during the installation of SETFOS. So if I click on the SETFOS, you can find this is a library of SETFOS, where multiple materials are given as an input. You can see here, this is complete database of some optical material and semiconducting materials. So mostly NK files are present in the library. If I scroll right side, you can find a lot of materials are there. Lot of materials as a input material database given in our library during the installation process. So you can see here, it is a huge database. If any material is not present, then you can also upload your own library. You can upload your own material in this database. The database is installed in the C drive. Because the software is also installed in C drive, you can see this path. This PC, window, program file, Fluxim, SETFOS 5.4, and this material. Inside this folder, the material database is there. This is the path of the installation of the software where mat folder is there. Inside this mat folder, each couple of materials are already available. So whatever material you want to use for your structure, you can search it here. I wanted to use ITO. So I press I and I can find here the ITO.nk file present. I can select it and click on open button. It is now added here. The refractive index is added and assigned with this ITO material. Then I can click on this ETL layer. You can see this is ETL layer. And similarly, the refractive index of electron transport layer is not constant. It is dependent on wavelength. And click on this constant option, click on file option, click on import options. And then which material you want to use as electron transport layer, you have to select that particular material. Let's say, an example, you want to take spirometrid. So I select this spirometrid and click on open to load it. So this is loaded as an electron transport layer. Then I click on perovskite layer. And again, I want to click on this constant, click on file, want to load the material from my library. Instead of creating the material file, I want to import from library. But if you want to create your own material, that is also possible. The user can give his own input. I click on this import, go to this perovskite folder. You can find it. There are multiple combination of perovskite given in the library. So whatever type of perovskite you want to use, you can take it. If the material is not present, perovskite, you have to add it. You can see these are different combination of perovskite material with different band gap. The material are added. Let's say example, I want to take this CH3NH3 PBl3. MAPI perovskite, I want to take it. I select it and load it. This is refractive index preview file, which is showing here. And similarly, if I click on this HTL layer, I can click on constant, click on file option, and click on import option. Here, let's suppose I want to use P3HT PCBM. So I select P3HT PCBM.nk file and click on OK. Now I click on aluminum, click on file option, and aluminum.nk file I want to open from my library. And now I have loaded it, and this is my air on the bottom sides. Now let's suppose the optical property. So I can give the test perovskite optical name of my projects and would like to do the calculations. If you want to see this absorption setting, by default AM 1.5 spectrum is taken. This is AM 1.5 spectrum. The red range is giving the spectrum range. And blue region, the range of wavelength that is specified by me. Default 380 to 780 default wavelength. If you want to change it, you can change this wavelength also, and it will change here. Okay, it will change here. So the wavelength range which we have specified, that is called in blue color, and total AM 1.5 spectrum, that is called red spectrum. So we can take the standard spectrum, AM0, AM 1.5, global spectrum, direct spectrum. If you click on this browse button, import file containing the wavelength and intensity. If I click on this import file, you can see multiple spectrum file are exist in our database. That stand for .sp extensions. .sp is the extensions of this spectrum file. .sp is the extension for this spectrum file. So you can load AM0, AM 1.5 direct or anything. If you have any spectrum, you can also load your own spectrum as well. The spectral shifting is possible. You can give your wavelength and intensity. If you want to check it, you can click on this preview button. The first column is called wavelength. The second column is called intensity. So wavelength is there and intensity is there. So you can take either wavelength or intensity. You can define here first column as wavelength, second column as intensity, and that spectral shifting is possible. So you can define, you can see here, this is called the reference. This is called the reference. Reference from where the spectrum is taken. This is the website from where the spectrum is taken. So if you have some data, you can also use it. From this reference, the data of this AM 1.5 is taken. If you have a wavelength and intensity graph, you can also create the .sp file, that is simple notepad file. So you can use here the file can be also loaded in our database if you already have some spectrum database. So it will not only use the standard database. Location and time specific spectrum is possible. So if you will click on this location and time, you can see the latitude, longitude, because the different location may have different spectrum. In Delhi, we have different spectrum. In Bombay, we have different spectrum. Kolkata may have different spectrum. Chennai may have different spectrum. So particular location, we can define it. Particular location, we can define the latitude, longitude, elevation, date, time zone, cloud, weather condition. We can define the azimuth, tilt on particular angle, the spectrum. So that the realistic condition, you can find how much that light will get absorbed. So that kind of scattering is also possible on particular location and time. Because night time may be low spectrum, daytime is heavy spectrum. So that kind of possibility is there. So that realistic condition, you can find your more accurate characteristics. Now you can see here, this is a absorption spectrum related parameter in this absorption module. I have assigned all the refractive index to each layer. Now I want to run the calculations. So once I click on this run button, the simulation will execute. Now the simulation is done. You can see it will show whatever the direct incident power, ETL, ISC value, optical efficiency, perovskite ISC value. So as an example, it is showing like that. If you want to see the absorption profile, that which layer the more light absorbing. So the air layer is there, the substrate is there, ITO is there, ETL is there, perovskite is there, HTL is there, aluminum is there. So based on the optical refractive index, you can judge that which at what interface you are getting more absorbing material, and then accordingly you can use that. And if you will click on this spectral, this is absorptance. If you want to see a layer specific absorptance, this is each material layer absorptance. The red one displaying the unipolar, this blue one that is called 0, that is showing the substrate line. If you want to see this ITO, that is green, which is on hiding something. If you want to see this perovskite, this layer second from the top, this layer is called the perovskite layer absorptance. So each layer absorptance is plotted with the color display it is plotting. You can also extract your data. If you will right click on it, you can save your data in the form of image. Save in the form of image. Your data can be saved in a PNG, JPG, PDF format. Also, if you want to save your data in the form of text format, DAT format, save this visible data. You can save in the text format, Excel format, or any format. The data can be saved. The raw data can be exported so that you can import in origin or any other third-party tools. So that's why you can see the absorptance, layer specific absorptance, reflectance, stack contributions for each layer, transmittance characteristics, like that. So this is like one of the optical things which we have performed. If you want to do the electrical calculation, you have to enable this drift diffusion module. So click on this toggle drift diffusion. And then if you click on this substrate, you click on this ITO, you have to define that which layer you want to use as an electrode, which layer you want to use as a semiconducting. So that information you have to give it. So if we click on these layers, you can see the ITO, then click on general option and define this ITO as electrode. I click on this aluminum, click on this general and as electrode. So ITO is electrode, aluminum as electrode. And in between that, I can define ETL as a semiconducting layer, perovskite as a semiconducting layer, and then HTL also as a semiconducting layers. So I have mentioned that ITO as an electrode type ohmic and thermionic, two options are given. You can see the work function is also there. Let me hide the right side layer structure so that you can see the visualized backend work function value. To enable the structure visualization, you can click on this visualized one. So ITO layer structure energy levels, it will display here. If I click on this ETL layer, which I have selected as a semiconducting, perovskite layer as a semiconducting, whole transport layer as a semiconducting, and aluminum layer as a electrodes. So that kind of things I have enabled. Now what I have did till now, I have defined the optical refractive index of my layers. But if I would like to define the semiconducting properties also for ETL layer, perovskite layer, HTL layers. So what I will do, I will click on this ETL layer and go to the semiconducting tab. previously we have defined the optical refractive index, NK data. Now, in between the electrode, we have to define the semiconducting materials. Semiconducting material in the sense where HOMO-LUMO will be there, dielectric constant will be there, density of state will be there, electron mobility will be there, hole mobility will be there, traps will be there, ions will be there. So that is called semiconducting. So either I can define manually by putting the value in the respective box, which you can see here. This is the respective box. I can define the HOMO, LUMO, density of dielectric constants. I can enable the acceptor doping and define the concentration, either constant or dependent on the positions with respect to file, acceptor type, donor type. So we have to enable that particular checkbox, and then we have to mention that particular value to define the doping type. Similarly, if I will go down, you can find the optical generation efficiency, state-of-art mobility models are there, some constant mobility model, field-dependent mobility model, field temperature-dependent mobility model. EGDM and ECDM is there. EGDM stands for extended Gaussian disorder, extended correlated disorder, field-dependent mobility file. So these mobility models can enhance the efficiency of your devices. So that's why we have to mention here mu E and mu P. Electron and hole mobility need to be specified. And if you want to click on this excitons, you can also add the excitons. Like you can add this, you can find the radiative decay rates, non-radiative decay rates, generation efficiency, Langevin, bimolecular, simplified, SRH, traps, trap, total recombination generation, diffusion constant, saturation, annihilations, triplet interactions, singlet interactions, energy transfer rates, total energy, TADF from low energy to high energy, exciton, polar and quenchings for electron and holes. So if you want to add the excitons, you can add it. If you click on these traps, you can see the bulk traps is there. You can enable the trapping. You can enable the SRH recombination for this material, enable trap recombination. So that particular checkbox need to be enabled. Single energy level traps are there, exponential density of state traps, Gaussian density of state traps. So these are the traps, these are the model parameter for single energy level trap parameter. And if you enable the exponential density of state traps for electron and hole, both traps are possible. Similarly, the Gaussian density of state traps are there. So this trap will be possible according to your convenience. If you go to the mobile ions, you can define the anions, cations, associate the mobility model with that particular anions and cations or ion transports. If you go there, you have to define the density of this ions, minimum and maximum up to infinite density you can define. If you go to the next step, that is called recombination, you can define the Langevin recombination, Auger recombination, bimolecular recombination, simplified SRH recombinations. So based on that recombination, you have to define the electron prefactor, hole prefactor, Langevin recombination efficiency, bimolecular prefactor, simplified SRH lifetime value, hole and electron lifetime value, total energy offset value. So you have to give that according to your convenience. If you want to enable the impact ionization for reverse breakdown, you can enable this impact ionization. And Chinovich model is implemented with Chinovich linear and Thornberg. These are different mobile electron ionization threshold energy, hole ionization threshold energy, and Thornberg impact ionization models are there. So this models will also help you to improve the ionization of impact of ionization in your device characteristics. Now, in the dip to diffusion setting, if you go the dip to diffusion for electrical calculation, you can find there is an option called dip to diffusion mode. Steady state calculation is there. Transient simulation is there. AC impedance is there, IMPS and IMBS, intensity modulated photocurrent and photovoltaic spectroscopy. So this DC AC transients all become possible in single software. So for DC, the default parameter will enable. We will select the transient signal, transient solver, and associated parameter will be enabled. Similarly, for AC analysis, the frequency related parameter, amplitude related parameter, IMPS related amplitude related parameter will be enabled. Let's assume we want to do a simple steady state calculation. Default voltage is there, let's suppose 0 volt, but we want to perform the sweeping. So click on the sweep mode. If you have any parameter that is unknown for you, you have no idea how much the input value of voltage, temperature, wavelength, refractive index, thickness, doping, HUMO-LUMO, dielectric constant, any parameter which is you are giving as input, that parameter is not known by you. Then you can perform the sweeping, where sweeping will help you to give the minimum and maximum, perform the optimizations. So let's suppose you want to perform this particular structure, voltage sweeping. So you can click on this voltage sweeping. You can sweep the voltage linearly, random, or any particular value. Multiple options are there for sweeping. Let's suppose from -1 to +1 with the increment of 0.2 volt. You want to run the simulation at -1 volt, -0.8, -0.6, -0.4, -0.2, 0, 0.2, 0.4, up to 1 volt with 2.2 increment. The software will run the calculations. Now this is optical plus electrical. And then click on start the calculations. So simulation is very fast. It will hardly take 5 minutes, 10 minutes, 2 minutes, dependent on the structure. And now you can see the current density. Lagrange recombination without any current density, it will plot like that. From minus to plus, minus value to plus value, -1 volt to +1 volt. Power conversion efficiency from -1 plus to +1 volt. Similarly, the device current, the device voltage and current, and this is Lagrange, multiple Lagrange without any mobility models. If you want to see the absorptance, this is for absorptance with the graphical form as well, from minus to plus with the wavelength as well. So layer absorptance is also there. Some electrical band diagram is also there. This is band diagram at -1 volt. If you want to see at -0.8, this is at -0.8, -0.6, -0.00 volt, 0.2, 0.4, 0.6, 0.8, up to 1 volt. So you can sweep the value and you can find the band diagrams. So all the charge carrier density plots, charge generation plots, current plot from negative to positive, how the current will flow, that current, displacement current, N-type, P-type current density, it will plot like this. This is graphical representations, and the potential can also be there from minus to plus potential. This is for potential graph. Recombination is there from negative to positive recombinations. As an example, it is calculated. So this is like way you can perform it. If you want to add multiple parameters at a time sweeping, you can click on this add sweep once again. And let's suppose this time you want to add the perovskite layer thickness. Where layer thickness you want to change from 20 to 200, 20 nanometer to 200 nanometers. So you can define the 20 nanometer and 200 nanometer with increment of 10 nanometers. So that's why it will perform 2 parameters at a time. It will perform 2 parameters at a time sweeping. So let me run the simulation. Voltage will be sweeping and thickness of perovskite layer will also be sweeping. The simulation time will little bit increase whenever the number of multiple parameters sweeping will increase. This is the software user interface, how easier the software is for modeling the structures, for running the simulation or visualization of your output. That I wanted to show you. Some realistic result I will show you in the example. So you will see the example after this finishing of this calculations. Since I have added two parameters, voltage and thickness, and value minimum 20, 200, 200 with 10 steps. So that's why on different value, the software is doing the calculations. So that's why 2 more minutes the simulation time increased. But still it is running on the laptop. So you can also get the result on normal laptop as well. As much as the system is good, you will get that more faster speed also. Now the simulation is done. You can see the device current with thickness variations. This is perovskite thickness variations from 200 to 20 nanometer to 200 nanometer thickness variations. Similarly, the power conversion efficiency plot. As an example, I have taken it. Electrical IV key figures. If anything is there, it will show display here. Band diagram is there from negative biasing, and thickness is also there. So this is a one procedure which you can plot the multiple analysis, multiple things. Now I want to show you some of the example. You can see in this left side. If I want to take one perovskite example, let's suppose this is one. You can see this is one another example which is given in the library. ITO, some metallic electrode, some perovskite, ETL, perovskite layer, HTL layer, C60, AG silver. They have created such kind of structure. And you can see the layer structure, energy levels. If you want to see the output of this particular, which is already simulated structures, you can find the layer absorptance, find the direct and incident power, normal incident power. It is basically a transient perovskites. I want to show this structure where glass substrate, FTO, TiO2, methylammonium lead iodide, spiro gold. This is one of the structures. Full perovskite IB, absorption AM 1.5, depth diffusion steady states, and voltage is sweeping -1, -1.1, -1.0, 0.98, 0.96, 0.94, 0.9, up to, you can see up to 0.1 volt. With each particular value, the voltage is sweeping. So let it run the calculation for this particular structure. You have seen the structure is there. Simulation is completed. You can click on this result window. Click on device current. This is IV curve with voltage variations. You can also take your data as well. If you want to see the log, you can also plot in the form of log your curve as well. Like that, so you can plot your data. This is for recombination, if any recombination is there, and this is for Lagrange recombinations. So you can plot your data from that voltage biasing. It is at different voltage biasing, the graph is plotted. If you want to see the display IV curve, this is electrical IV key figures. VOC is calculated, GSC is calculated, fill factor is calculated, maximum power test is calculated, power conversion efficiency, maximum power conversion efficiency. This is electrical key figures that is calculated. You want to see the power conversion efficiency. This is for power conversion efficiency. If you want to see the electrical profile band diagram, this is band diagram. FTO, TiO2, Mali, methylammonium, lead iodide perovskite, spiro, and gold. So negative to positive band diagram. Okay. Similarly, you can see the LUMO characteristics, FUMO characteristics, and energy reference Fermi level for N type and P types. And this is electrical fields. And this is electrical field characteristics. This is recombinations. If you see here, other photocurrent is also there. The value of photocurrent for TiO2. TiO2 is 0, it is showing. Methylammonium lead iodide, this is photocurrent. And for Spiro also, if anything is there for Spiro, you can see for the Spiro, if anything, the photocurrent is displaying. The two graphs are overlapping to each other. You can see this is stack contribution, passive optical analysis, solar eye integrated analysis, and some spectral from negative to positive, if any variation is there. Let me take some other example. So if you see here, this is another example of full perovskite solar cell. In this particular example, the air, glass, ITO, MOO3, CY7P interface is there. Electrical exciton interface is there. Top, bottom diffusion length, generation efficiency, hopping models are there. Interface stress, interface recombinations, C60, ALQ3. This is multiple. There are two semiconducting layers in between electrode with the interface is also there. So root mean square setting is possible. Voltage is sweeping from -1 volt to +1 volt with 0.1 increment in this particular device simulations. So let me run the calculation. Simulation is done. You can see the IV, current voltage curve with Langevin recombinations and without any recombinations. The device IV curve. Data, you can click on this save visible data, and you can save on desktop. Let's suppose IV curve. The name of this data I want to save. Click on save, and data will become saved in my desktop, which I have extracted. You can see the first column is voltage. The second column is called current density. Third column is recombination current density. And fourth column is Langevin recombination current density. So from -1 to +1 volt, the data is extracted from this particular graph. The data is extracted. Similarly, the power conversion efficiency and power density. And other electrical profile is possible that I already explained you. For more number of layer structure, if you want to see the 10 layer, 20 layers, I would like to show you the structure. 1 minute. This is called you can see here this new structures. In this particular structure, how many layers are there? Air there on the top, MgF2, top ITO, SNO2, C60, perovskite, nickel oxides, interface, middle ITO, amorphous silicon N-type, amorphous silicon, intrinsic buffer layer, N-type buffer 2, and this is some HTL and bottom ITO layers. You can add more number of layers also. Light side, the layer structure and their energy levels. So, and sweeping, voltage is sweeping this particular case. If you want to see the output, you can see the device current output is there. This is IV curve for multiple recombinations, simplified SRH, Langevin, bimolecular. And you can also export this data. So interface SRH current with voltage graph, power conversion efficiency, particular volume, power density, and you can click on this band diagrams. In the band diagram, if you will zoom particular regions, this is particular zoom region is there where band diagram can be visualized. the interface between different materials. I have zoomed particular regions and you can see like that. If any variation is there, you can see how the band diagram is varying, changing. So similarly, the current density plots and many properties are there, the software can calculate. Still, if somebody want to perform or texturing, ray tracing, these are some another example. And if you want to see the quantum efficiency, this is one of another example, P dot, P3HT, PCBM, aluminum. I can right click and click on run button. Now you can see whenever the number of sweep steps are more. In this particular example, there are two parameters sweeping, wavelength and voltage. Wavelength from 300 to 800 with 2 step size. That's why the time is more. So we have seen the simulation is done. If you want to see the AC amplitude, AC EQE, amplitude curve, AC curve with the voltage variation, with voltage from negative to positive, responsibility, AC responsibility for photodetector, responsibility power curve, and other electrical device current value with wavelength variations with respect to wavelength. If you want to see the quantum efficiency from negative to positive, this is quantum efficiency. External quantum efficiency graph here. Photocurrent, if you want to see, this is for photocurrent. With wavelength, at what particular wavelength the photocurrent will be more. That study you can see here. From negative to positive biasings. Similarly, this is for EQA. If you want to see here, the quantum efficiency. This is quantum efficiency. This is for quantum efficiency. This is for device curve with wavelength variations. And if you want to see a solar energy yield generated power, I can show you. This is one of another optical calculation only. In this optical calculation, the location and time specific spectrum is used. This particular latitude, longitude, and let's select the date and time. This is previous date and time is selected. I want to choose it. Let's suppose my current date and time. Let's suppose we want to see from today. Here I can see this is from start and date. I can select here from which date to which date you want to see your light absorbing things. So based on theoretical models, it will predict the device. So I have selected this and then go to the next. Start date, end date I have selected and click OK. And with 1 hour interval, I want to run the job. Solar energy yield calculations. Simulation is done. Now you can see on 28th May, how much will be the energy yield, cumulative 29th May, 10th May, or generated power in daytime, evening time, incident spectra. This is for incident spectrum, direct spectrum, diffuse spectrum. So the diffuse spectrum area, solar angle is there on tomorrow, day after, next day after tomorrow, and next day. So the solar angle, energy yield, incident power, photocurrent, on which day or time the photocurrent will be more. that study can also be performed. So if I will say you the conclusion, the software is very broad and a lot of functions and features are there. And I can assure you, the software will help you a lot for learning the capability. We have many things to explain about the capabilities, including for LEDs also. If you talk about the scattering quantum dot, this is for down conversion quantum dot also. For texturing nanoparticles, you can see this is for texturing nanoparticle retracing analysis. So retracing, texturing, monodispersion, polydispersion, Gaussian dispersions, scattering for advanced optics module will be required. For quantum dot phosphorant dye as a material, down conversion layers you can use. That kind of functions is possible. And this is like even other application, LED is also possible for emitting devices. So let me show one example of LED. Then we'll take your questions and answers and we'll finish the demo. You can see this is another example. Anode and cathode gold is there. HTL, 2 emitter layer are used. You can use 1 emitter also, but in this particular 2 emitter are used, full doped OLED application. So dependent on your modules, you can plan that which module is required for your particular application. Now you can see the simulation is done. Reflected color, emitted color, intrinsic color. This is electrical key figures, excitons, iterations, EQE value is there, optoelectrical calculations. And this is for band diagrams. You can see the band diagram is there. Current density plot is there. Recombination plot is there. And if you want to see the emissive CIE color diagram, this is for CIE color plot. Including if you want to see the emission spectrum, this is for emissions. Normalized emission, white emissions, absorptance, reflectance, transmittance, radiative dipole density, radiative decay rates, and many more things are there to explain for you. So you can see this is another one of the example for different applications. If I will see here, this is ITU, MT data, alpha NPD, BLQ, TPBI, LIFAL. And here you can see other characteristics, luminous efficacy and some optoelectrical calculation, device efficiency like that, generated photons, EQE, and emissions also, temperature dependence emissions. And this is even more complex structure for white OLED with filters. So reflected, emitted, intrinsic colors and some CIE color diagram is there. If you want to see the impedance related characteristics, I can show you one impedance IV. Nyquist plot, let's suppose this is one of the example, gold, MEH, PPB, calcium. That we run the calculation for this particular impedance analysis. Simulation is done. You can see the AC current amplitude, AC current phase, AC current, capacitance, conductance, impedance. This is for Z. Red graph is impedance Z and Z0 with respect to voltage. If you want to plot the Nyquist plot, you can export your data, save this data, visible data, Nyquist plot Z and Z0. You can also plot from here. and click on the save. And you can see the first column is voltage, second column is Z and Z naught, real part and imaginary part. And these two vertical columns, second and third column, you can plot the Z and Z naught Nyquist plots. So that's why the software can help you a lot for DC, AC and transient simulations. So from till now, I have tried to explain many things about the software. There are 10 minutes are remaining. If participants have any questions, you can unmute your mic and you can ask your queries. We have a YouTube channel also, so that you can watch some more videos which we have delivered previously about this software. So I want to show you my YouTube channel, where we regularly post our information about different softwares related to nanotechnology, semiconductor, quantum technology. All are available, even related to SETFOS also. You can see this is different product that we provide. So by this name, Impulse Technology Innovative Research, you can search in your search bar and you can fetch this channel and find more meaningful insight, case study or webinars, demo, presentation, which we organize past for other participants. So on different application, we have organized this different demo, even for SETFOS also. If you want to see, go to the playlist, and in the playlist, you can find the SETFOS. It is here. All SETFOS, NanoDecal, Device Studio, Rescue, QTCAD, all software. The same particular domain, we are working on it. So you can watch these video and learn more about the capabilities. So thank you for giving your time and attending the session. If participants have questions, you can unmute your mic and you can ask your questions, please.
Good evening, sir. As like in our humanities research work, we are utilizing SPSS software. So as like in your research work, you had utilized this particular software or you had also used the SPSS?
Which software, SPS?
Sir, it's statistical package for social sciences. So had you utilized it also in your research work or not?
No, basically we have not used that software. We are specifically working for SETFOS Luxembourg.
Okay. So you had just utilized this particular software and collected and gathered all the data, right?
Yes, we get the data and we provide the software. We sell this software as well.
Okay, so can it be downloaded from our Play Store or from anything else? Can you please share the link?
No, there is, you have to I can share you. I have already given the information. So this is a commercial software license version which need to be purchased. If the funding is available, then we can also provide you the trial version.
So sir, in my advice, it is just an advice to you. So can't you apply for the research grant or funds available on the ICMR portal, etc., etc.?
So you can apply for funding to DST or by the institute. Basically, institute purchase the software. We have supplied the software in Berhampur University, where madam in the first session that delivered the talk in their papers. He purchased it and published some paper. Similarly, if somebody is interested, we can you can plan by your institute.
If I am interested in later on moment, I will definitely contact with you. Right, sir? Okay. Thank you so much, sir, for the session.
Thank you.
So what is the financial for that? I mean, what will be the price?
Basically, we have a multiple options. As like we have a based on the one thing is based on the module, which module is required for you. As the software is divided in 4 modules: absorption, depth diffusion, emission, and advanced optics. How many modules are required, and for how many years the software you have required? For 1 year, 3 years, 5 years, 10 years, dependent on the validity and module. we have different options. So minimum package that we have, yeah, please.
No, please.
So basically we have like, if you will go for 2 module, only absorption and advance of takes for 1 year, that will cost around 3 to 4 lakhs in between. 3 to 4 lakhs.
Okay. And that include your support also.
Yeah, support also will be provided.
Okay. If 1 year we wish to get all the features that the software has, then
Then around 4 to 5 lakh